So, hello students, let's continue our discussion on the amplitude modulated waves. In this lecture, we will study about the generation and the detection of amplitude modulated waves. Now, the idea behind the generation of amplitude modulated waves is that we add the baseband signal or the message signal with the carrier signal and pass through a non-linear device. For example, diode is a non-linear device. And then pass its output to a band pass filter of suitable central frequency to obtain the desired modulated wave. So for this purpose, there are two methods. One is coil law modulator and second is switching modulator. Let's discuss this one by one. As we know, for small voltage variations, the diode acts as a non-linear device. Suppose, so if we draw the IV characteristic of the diode, it is somewhat like this. So in this way, the output voltage V2 can be represented as a non-linear function of the input voltage as V1t plus square of, sorry, this is V1t, where A1 and A2 are system properties. And V1 is the addition of the carrier wave as well as the message signal. So let's say if we write CTS, where FC is the carrier frequency, then taking common here, can write Now writing the constant and taking given outside here, if we write AC equals to A1 into AC dash and thus define the term voltage sensitivity comparing with the standard equation of the modulated wave. So the voltage sensitivity we have discussed this earlier. Finally, this represents our desired amplitude modulated wave. All we have to do is to pass it with a band pass filter with a sufficient cutoff frequency. So we can write it once more. Now we have to pass the same signal to a band pass filter. Now you can see here what types of frequencies are present here. This is our required modulated wave frequency, and so if we represent the same on the frequency spectrum of P to T, you can write on the frequency domain. So this is our desired modulated wave. Its representation can be shown like this. And let's say if let's say this is the nature of our baseband signal with maximum frequency FM. Symmetrically over the negative frequency. Moving on, this is our baseband signal. So on the frequency domain, similarly, this component has a frequency of 2 times of f of c. So if we extend this axis a bit forward, then we can represent fc. So 2 times of fc, 2 times of fc, and here will be minus 2 times of fc. In terms of the delta function, and corresponding to this, the magnitude at the zero frequency. So it will come from what? It will come at the origin. Further here, frequency is 0, and the rest we are left with m square t, or mt multiplied by mt will give a 2 times of the frequency, the maximum value of the frequency. If it has got a frequency fm maximum value, then it is situated around the zero frequency. So it can be drawn somewhat like this. So this is the frequency spectrum representation of the output signal V to T. Now all we are interested in this signal. This is our signal of interest, which is present in this portion of the spectrum. So we will apply a band pass filter here of central frequency fc to obtain the desired modulated wave. So this is the circuitry of the band pass filter. We have to tune the band pass filter to a very sharp cutoff frequency in order to obtain the desired amplitude modulated wave. Now, the limitation of this method, that is the square law modulator, it can be used only for low power variations. Or low voltage variations. Because as we know, if this is the for a non-linear device like diode, the non-linearity is obtained on a very on a smaller portion of the curve. And second thing, you would require a band pass filter with very sharp cutoff frequency. Now if we see here, this portion, so we have to apply a band pass filter here whose lower frequency must be Fc plus Fm. Then you see this should be Fc minus Fm and this will be Fc minus Fm because this is Fc plus Fm, so this should be Fc minus Fm. So it should be such. Now this frequency spectrum, which has a maximum frequency of 2 Fm, and this is a band pass frequency of our interest. Now these two frequency spectrums should not overlap. Otherwise, the filter will suffer distortions. So, if you see here, then its lower cutoff frequency of the band pass filter, which is Fc minus Fm, it must be greater than 2 times of the maximum frequency of the wave, of the message signal. We can write here that is Fc minus Fm must be greater than, then Fc must be greater than at least 3 times of the maximum frequency present in the message signal. So these are certain limitations of the square law modulator. Next, move on to the second type of generation called the generation method, switching modulator. Earlier we had utilized the square law characteristic of the diode, but here we will utilize the switching characteristics of the diode. As we know, Any diode in the forward bias, it has a straight line characteristic or the linear characteristic. This is V out. That means input will be, the output will be equal to the input voltage in the case of forward biasing, and for negative values of Vt, 0 in case of the reverse bias case. So it has a switching behavior. So let's draw the circuitry behind the switching modulator. Once again we will do the addition of both the waves. The pre-assumption behind using the switching modulator is that the absolute value of MT must be much less than the peak amplitude of the carrier wave. It is given as AC cos 2 pi FCT. Then only we can implement switching modulator. Since the absolute value of the message signal is much less than the peak amplitude of the carrier wave, then the switching characteristics of the diode will be governed by the carrier wave only. We can write here. This implies that the switching of the diode will depend on the polarity of carrier wave CT only. If we see this equation, we can say that V2T will be equal to V1 in the case of forward biasing it will equal to given t only when Ct is greater than 0, and when Ct is less than 0, that is the case of reverse biasing, its value will be 0. Also Vt is nothing but the sum of Ct and Mt. In that case, so once again we can write V2T is equal to V1T times of Xt, where Xpt will be a wave whose value will be 1 for when Ct is greater than 0 and 0 for Ct less than 0. Suppose we draw if we draw Ct, which is a cosine function, we are drawing a rough sketch of Ct. Ct is a cosine function. Just drawing a rough sketch, and similar, then the signal Xpt will have a value 1 when Ct is greater than 0 and 0 when Ct less than 0. We can draw the signal Xpt. So for positive values, its value will be 1, and for the negative values, its value will be 0, and so on. Just repeating the signal. This will be the curve of Ct, whose value is 1 when Ct is greater than 0 and 0 when Ct less than 0. Now we can see that this is a This is the periodic signal. We can represent this signal in terms of Fourier series summation. Now, this is similar to the square wave whose Fourier series summation we have derived earlier in discussions in signals and systems. So we know that if this is our square wave whose amplitude is 1 and minus 1, then we know that its Fourier series summation is given as ft equals to summation 4 upon n pi sine n times of n omega ct, where omega c equals to 2 pi fct, n equals to 1 to infinity, and we know that square wave takes only odd harmonics. N is equal to odd. It will take only the odd values 1, 3, 5, 7. Now, if you see these two signals, if you compare these two signals, then this signal is shifted. This signal is square wave. It is a square wave shifted vertically by 1 by 2. Just shifted vertically. Sorry, if this is let's say this is 1 by 2, make it 1 by 2, then this its amplitude will be 1 by 2 only, right? So if you want to add one thing more, it is shifted vertically as well as it is shifted leftward by an angle of pi by 2. You can see this signal for this is a square wave. This is right now this is an even signal, and sorry, this is an odd signal, and this is an even signal. Then if you closely look at this signal, then if you shift this signal by distance t by 4, suppose its time period is t by 4, then you will get this curve xpt. How? Because shifted by an angle pi by 2, because omega t you are shifting by 1 by 4, then omega in terms of angle if you write, that will be omega t by 4, which is 2 pi by 4, it will be pi by 2, pi by 2. So if we want to write the equation or the Fourier series summation of this signal, we can simply write it here. We will do the shifting vertically as well as in the left side direction. Also here shift by pi by 2 leftward. So two types of transformation we are doing. Shift ft upward by 1 by 2 and shift ft leftward by angle pi by 2 radians, right? So if you want to write, now if you want to write the equation or the Fourier series representation of xpt, we can write if we look this equation here, this equation is shifted upward by shifted upward by 1 by 2 units, then we can write it here 1 by 2 plus summation of, and this will be 2 by n pi sine n omega c t n equals to 1 to infinity, only the odd values, plus we are giving a leftward shift of pi by 2, so there will be a leftward shift by pi by 2 radians, and we can write here 1 by 2 plus summation 2 upon n pi sine n omega c t plus pi by 2. So taking the fundamental component outside, we can write 2 upon pi, and this sine will become cosine because of a phase shift by pi by 2, cos, and omega c will be written as 2 pi fc into t, and plus this is from 1 to infinity, then but this will be from n equals to 2 to infinity, only the odd values, 2 upon n pi sine this will be cos 2 pi fct, or then v2t will be v1t times of xpt, then we can write the output voltage v2t as v1t into xpt, and v1t as we know is ct plus mt times of xpt, and this is our xpt. We writing ct is ac2 pi fct, sorry, this is cos of plus mt, and xpt is given half plus 2 upon pi cos 2 pi fct plus summation n equals to 2 to infinity 2 upon n pi cos 2 pi fct and you have to multiply here n for nth harmonic. We have left here n, it will be cos n times of 2 pi fct. So once again, writing V2T as AC. Let's take only the desired components. This is our desired component. This will be AC 1 by 2 cos 2 pi fct plus mt into 2 by pi cos 2 pi fct plus other terms. As there are infinite terms are here, there will be, so just write it as other term. We are only interested in this term because this is the form of the modulated wave, modulated amplitude wave. So V2T can be written as, if you take AC outside, C by 2 outside, then it will be 1 plus mt times of, let's say, Ka cos 2 pi fct plus other terms. Where you can write Ka as 4 upon pi into AC. Right, this is the voltage sensitivity. So looking at this equation, this is the desired modulated wave, and by choosing a band pass filter of desired frequencies, we can generate the modulated wave. Now the advantage here is that, one important advantage is there, it can be used over larger voltage levels, unlike the square law modulator. Second, the band pass filter requirement is not as stringent as in case of square law modulator. So these are the two methods of generation of amplitude modulated waves. All we are doing is the summing up the message signal and the carrier wave and passing through the nonlinear device. This nonlinear device has both a square law characteristics, which is used in the square law modulator, and as well as the switching characteristics that we have applied in the switching modulator, and then finally applying a band pass filter of suitable cutoff frequencies to finally obtain the modulated wave ST. Now, this is now ST can in general can be written as AC times the 1 plus Ka into mt times of cos 2 pi Fc into T. This is the form of the modulated wave. Now, we have seen the generation of the amplitude wave on the sender side. Now let's see how this wave is demodulated, or you can say we want the message signal back in its original form. So let's see how we do the demodulation, or you can say the detection of the amplitude modulated wave on the receiver side. For this, there is one method called envelope detector. As we have seen that the message signal resides on the envelope of the carrier wave. Then with the help of the envelope detector, we will try to trace the envelope of the modulated wave. Let us again draw the graph of the modulated wave. Let's say if this is this is the envelope which contains the message signal, and this is oscillating with the carrier frequency. We are drawing a rough sketch. This is the modulated wave ST. Now our job is to recover back the message signal, and the message signal is contained on the envelope of ST. So the green curve is the message signal. Now, since we are trying to trace the envelope that contains the message signal, that is why this detection method is called the envelope detection method. We say envelope detector because the envelope contains the message signal empty. Let's draw the basic circuitry behind this. Let's say this is the incoming modulated wave at the receiver end. Let's say this resistance is Rs. This is the ideal diode. This is the capacitance C. This is Rs. Say this is the load resistance. Once again draw ST here. Let's say this is now the envelope is the message signal ST. We have drawn the rectified form of ST because this diode will work in the forward biased. It is basically acting as a switching device, unlike the non-linear device that we saw in case of the square law modulator. This will only act as a switch in the forward bias zone. Now see here, in mode 1, when the diode is on or in the forward bias mode, what will happen? This capacitor, which is initially uncharged, will start charging. Then if we write the, so if we let's say we draw the voltage across the capacitor, it will start charging. Now once it has charged to a value which is greater than the peak value at that instant of ST, then the diode will become reverse bias, mode 1 D on, then this is the case, the charging case, mode 1. Now what will happen? Now this has become open circuit because the capacitor has charged. Let's say this is VC. This point is VC, this node is VC. RS is a small resistance. So that we can write here as ST. This point is, then it has charged to its peak value. Now VC, when VC goes greater than ST, that is it has reached to its peak value, then diode will go off. Okay. So in mode 2, D is off. Then this circuit will be an open circuit. Then capacitor will start discharging through the resistance RL. Then there will be a discharging period. And once again, when the discharging, when ST goes greater than VC, discharging has been done enough so that the amplitude of ST at that instant of time goes greater than the capacitor voltage VC. Again it will start charging. And hence this charging discharging will continue until the envelope has been traced. Now you can see the curve or the voltage across the capacitor is roughly trying to trace the envelope. You can write here the capacitor voltage traces the envelope which contains empty. This is the envelope of ST which is the desired trace or curve of the message signal empty. Right? So if we write it, if we write the curve, the trace of the curve separately, once again from this, uh, till something like this, and it is approximately equal to the trace empty. This is VCT. So this is how the envelope detection is done. Now the thing is that now there are modes of charging as well as discharging. Then the idea behind the envelope detector is that charging time constant must be very low, and that means it should must charge very quickly during the on period, and discharging time must be higher. Now why is this? So let's say tau is the charging constant. So during the charging is done through the resistance and the capacitance. Then tau charging time constant is Rs into C. Then this charging constant must be very low, and it should be Rsc should be much less than the time period of the carrier frequency. Second thing, during the off time, when the diode is in off mode, when the discharging is taking place, the discharging must not be very high, otherwise it will discharge quickly. It should discharge very slowly, so as to trace the envelope very well. Now during the discharging is done through the resistance RL. Then the time constant discharging is RL into C, and the thing is that the discharging must not be very high or very low. It is given by that the discharging must be the discharging RLC, the discharging time constant must be greater than the time period of the carrier frequency, and also it must be less than the maximum rate of change of the maximum frequency contained in the message signal. So we can write it here as upon Fc, which is the RLC, the discharging time constant, Ri into C. So these are the charging and discharging conditions for the smooth tracing of the envelope of the ST, and it is only envelope detection can be done only for under modulation case, for mu less than equal to 1. So these were the methods of generation and detection of the amplitude modulated wave. Thank you.